So, when you're dealing with NoSQL databases, the whole idea of eventual consistency really comes into play. You don't have the same guarantees that you get with SQL's ACID properties.
But isn't eventual consistency good enough for most applications?
It can be, but it depends on what your app needs. With SQL, you get strong consistency right away, atomicity, consistency, isolation, durability, all wrapped up in a neat package. NoSQL systems often trade some of those properties for scalability and performance.
That's true, but doesn't NoSQL allow for more flexible schema designs which can be advantageous in certain scenarios?
Absolutely, flexibility is a big plus. But let me ask you this. Have you ever had to deal with a situation where data was temporarily inconsistent? I remember once we deployed a new feature, and suddenly our logs were showing conflicting states.
Yeah, that sounds like a nightmare scenario. But isn't there a way to handle such inconsistencies through application logic?
There are ways, like using compensating transactions or implementing your own conflict resolution strategies. But it adds complexity. And then there's the CAP theorem. Eventually consistent systems prioritize availability over consistency, which means under network partitions, they might give you stale reads.
That makes sense. So ACID compliance is crucial in financial applications where every transaction must be perfectly reliable.
Exactly. In finance or any domain where precision is critical, you need that level of assurance. Even though NoSQL offers great benefits like horizontal scaling and handling large volumes of unstructured data, sometimes those trade-offs aren't worth it if strict consistency is non-negotiable. Right? So let's talk about the CAP theorem and how it impacts the design choices between SQL and NoSQL databases. The CAP theorem says you can only have 2 out of 3: consistency, availability, and partition tolerance.
That sounds like a tough choice to make.
It really is. Traditional SQL databases tend to favor consistency and partition tolerance over high availability. They ensure that all nodes see the same data at the same time, even if it means slower read operations during network partitions.
But doesn't that limit their ability to scale horizontally?
Definitely. Scaling a traditional SQL database horizontally is challenging because maintaining strong consistency across multiple nodes is resource-intensive. On the other hand, NoSQL databases often prioritize availability and partition tolerance. This allows them to handle more reads and writes by relaxing the rules around immediate consistency.
So does that mean NoSQL databases are better suited for applications that require high availability?
Generally, yes. For example, web services or social media platforms might choose NoSQL because they need to keep serving requests even under heavy load or network issues. But again, it depends on your specific use case. If your application can tolerate eventual consistency and benefits from horizontal scaling, NoSQL could be a great fit.
Makes sense. So choosing between SQL and NoSQL ultimately comes down to balancing these trade-offs based on what your application needs most.
Exactly. It's all about understanding the requirements of your project, whether you need strict consistency, high availability, or something in between, and then picking the technology that best supports those goals. That's a great point. Now, let's talk about eventual consistency and how it's implemented differently in SQL versus NoSQL systems. In NoSQL databases, eventual consistency is often a core design principle to achieve high availability and scalability.
So how do NoSQL systems ensure eventual consistency?
They use various techniques like asynchronous replication, where updates are propagated to all nodes eventually, even if not immediately. This allows the system to remain highly available during network partitions or node failure. However, in SQL databases, the concept of eventual consistency isn't as prevalent due to their focus on strong consistency.
But don't some modern SQL databases also implement some form of eventual consistency for certain operations?
Yes, some distributed SQL databases do offer mechanisms for eventual consistency, especially when they need to scale out across multiple nodes or regions. For instance, they might use techniques like multi-master replication or distributed consensus algorithms to manage data synchronization.
That sounds complex. How do they handle conflicts when implementing these techniques?
Good question. Conflict resolution strategies vary but typically involve things like timestamp-based ordering or application-specific rules. In NoSQL systems, you might rely more on client-side logic to resolve conflicts since the database itself doesn't enforce strict orderings. In contrast, SQL systems often have built-in mechanisms to maintain atomicity and avoid conflicts altogether.
It seems like both approaches have their pros and cons depending on the use case.
Absolutely. The choice really depends on whether your application can tolerate temporary inconsistencies and how critical immediate consistency is for your business logic. Understanding these differences helps in making informed decisions about which type of database to use. Exactly. Now, let's dive into the strong consistency guarantees provided by relational SQL databases. These guarantees are fundamental to many applications where data integrity is paramount.
What exactly do you mean by strong consistency?
Strong consistency ensures that once a write operation completes successfully, subsequent read operations will always return the updated value. This is crucial for applications that cannot tolerate temporary inconsistencies. SQL databases achieve this through mechanisms like locking and transactional isolation levels.
That sounds robust, but doesn't it come with trade-offs?
Indeed, it does. Achieving strong consistency often means sacrificing some performance and scalability. For example, in a distributed SQL setup, ensuring that all nodes agree on a single version of truth can introduce latency and complexity. However, this is a trade-off many businesses are willing to make for critical operations like financial transactions or inventory management.
So how do SQL databases manage to keep everything consistent across different nodes?
They use sophisticated algorithms like two-phase commit or paxos to coordinate transactions across multiple nodes. These protocols ensure that either all parts of a transaction succeed or none do, maintaining the ACID properties, atomicity, consistency, isolation, and durability that are essential for reliable data processing.
It seems like these guarantees make SQL databases more suitable for certain types of applications.
Absolutely. Applications that require immediate visibility of changes and strict adherence to business rules benefit greatly from the strong consistency provided by SQL databases. Ensuring that every piece of data is accurate and up to date is crucial in domains where mistakes can have significant consequences.